Okay, so let's start today's lesson. Now, so there are a couple of things I have put here as preliminary. So these things you're supposed to know. If you don't remember by any chance, maybe you should today go back home. So review these things. You will need these things, some of the things today, and maybe for our next couple of lectures. So basically, functions you should know, obviously, and specifically when you say functions, you should have some good idea about what is continuous function and what it means to say function is differentiable, and what is to say function is integrable. Okay. Completing square, something you studied in your school, grade 10 maybe. So this means when you have something like this, so you should know how to write this in this form. Method of partial fractions. So there are, I think again, something you have studied in school. Partial fractions you have used in semester 1 as well when you did integration. So which means if you have something like this, so when you want to separate this into this kind of form, so how should you do that? In integration by parts, we will going to need this heavily. So if you have two functions, f and the other function g as a derivative, so or the other form, whatever the form you familiar with. Then for differential equations, so this is the topic we stopped our things in semester 2. So specifically we looked at first order equations and second order equations, and I think mostly you will need second order equations. So second order constant coefficients, so both homogeneous and non-homogeneous. So you should know pretty much everything about these equations. So there's one thing I think I should mention something else about these videos. Now, I may do screen recording. Clear that part. Now, one question maybe you have why you have to study this. Now, obviously you are engineering students, and the answer will be apparent to most of you. So the required mathematics. I will give you briefly some idea. So what are the applications here? So applications of Laplace transform. So one main application, well, basically this comes in ordinary differential equations. So why ordinary differential equations are needed? So whenever you want to work with any physical systems, right? Say any physical processes. So now as a solution procedure, can make things much easier. Okay, so this is one main application, ordinary differential equations. Another application. So if you are a mechanical or electrical engineering students, you will see this later. There's something called LTI, so linear time invariant systems. So this is very important topic in electrical engineering. So again you will see Laplace transform appearing there. And this is also related to Fourier transform, again related to but the thing here to okay, so now at least you know why you have to learn this. Now the next thing is, if you remember, well, you studied something called definite integrals. So if you remember, so definite integral was something like this, right? So now what does this mean? Continuous function, and this is the area between the x-axis and the function from the vertical line and between vertical lines x equal a to x equal b. So which means it may look like this. So this kind of thing, it may be a here, b here, so this is f, and this is the area, right? So now if I make one limit at infinity, so then how are we going to do this? Say a to infinity f of x dx. So you should see, you cannot draw a picture now, because both limits also can be infinite, so this kind of integrals are known as improper integrals. So what we do, we define this integral, say take the function f of x, and let's say for simplicity I'm starting from a, and I integrate some value which is greater than little a to here, right? So e is like now this little capital A, and now you make this, once if this integral exists, now it does because the function is continuous, and you make this so you make a star, so which means you can take a limit, so as this a goes to infinity. So this is exactly what the definition for this quantity. Okay, so that's what is written here. Improper integral, this is how we define it. So if this limit exists, so which means then the integral converges to that limit, otherwise we say it diverges. Okay. So at the very beginning I can tell when we do things in limit, all things Okay, now for me, let me start with p equals 1 here. So we want to find 1 to infinity. So when p equals 1, this is 1 over t dt. So if you follow the definition, then we are replacing this infinity by the constant, say a, so 1 over t dt. Then we want to take a limit as a goes to infinity. So antiderivative here, logarithm t. So limits, lower limit 1, upper limit 10. This is logarithm a. So logarithm 1, so this is 0. So basically we want to know logarithmic function, as a goes to infinity, what happens to logarithm a? Now logarithmic function, if you remember, it goes to infinity, right? So which means this limit is infinite. So why is that? If you don't remember, so this is x. So logarithmic function is like that. Okay. So x goes to infinity, logarithm goes to infinity. Okay. But here note that the initial function we integrated is 1 over t. So our concern here from 1 to infinity, so let me write t here. So 1 over t may look like something like this. Okay. So when 1, let's say 1 is here, so 1 is here. Now what this tells, so we are finding area from 1, x equals 1 vertical line to above x-axis below the curve to infinity. So what we are saying is this area is actually infinity. Note that function goes to 0. Like 1 over t limit is 0, but still this area is so this means even though the function 1 over t, so the function is increasing. Even if coming over 0, but it does not come more than half. Okay, so how about when p is strictly less than 1? So 1 to infinity, this is t to the minus p dt. So this is t1 minus p over, okay, so if you do with limits, so 1 minus p does not depend on here, so we can take that part out. And once you put limits here, so upper limit, so when t equals a, you have a to 1 minus p. So minus, this is 1. So 1 to 1 minus p is 1. So this is what you have. So now that p is strictly less than 1, so which means 1 minus p so 1 minus p is strictly greater than 0. Okay. So now a is a large number. Right? Now you should understand what the limit is. So a is a large number. So a goes to infinity and a is from a to some possible. Quantity becomes large and large, so this limit is infinite, and after that if you subtract 1 doesn't matter, divide by 1 minus p, another positive number doesn't matter, so this limit is infinity. Okay. So case 3, so p is strictly greater than 1, so this means 1 minus p is strictly less than 0. So here if you do the things, it will be actually calculations will be similar to here. So 1 to infinity t minus p dt. So note that everything will be similar until you get this point. So because of that, I will write similar to above. So you have 1 over 1 minus p. So this is the quantity you have now. So now note that 1 minus p is negative now. Okay. So m is becoming larger and larger, and the negative, this limit is 0. So this will become 1 over t minus 1. So at this point, if you realize the integers are already. So because now the answer is p is p greater than approximately p is 2. Answer is 1. Integrals. Now for example, let's say when p is 2, so then you have say y equals 1 over t squared, right? So if you graph this, so you will get something like this. So we are concerned about from 1 to infinity, so value here is 1. So y equals 1 over t squared. Now this area is actually 1. Okay. So this area is finite. But here you should see this area was infinite. So that's why this is a serious thing you have. So in our earlier this terminology convergence and divergence, so you can summarize here final conclusion. So this is integral 1 to infinity t minus p dt. So this diverges if p is less than or equal to 1 and converges so if p is strictly greater than 1. Okay, now another something called exponential order. So what do you do with it? What do you now, so we say when you have a function, some function, so function f is of this exponential order as t goes to infinity if there exist constants k, c and t such that this is absolute value of f less than or equal to k exponential ct for all little t greater than or equal to capital T. So we want to find whether we want to decide each of these functions are exponential order or not. So I already told. So if you t squared, so it's second degree polynomial. So this must be exponential order, right? Maybe you can guess are these are exponential order or not. Decide this. So if you take the first one, so we take the given function, which is t squared, and divide this by some exponential function, let's say exponential ct. Okay. So while we do this, now once you do this, you should see I am dividing by exponential ct. If I can get something, some k here for my right hand side for large t, then well I can conclude this is exponential order. So to decide that, for large t we want to know the behavior of this ratio. What can we do? So we can take the limit, so as t goes to infinity. Now limits you studied exactly like 1 year ago. This may be the time to use it. So can you find this limit here? So how do you calculate this limit? Now maybe there are a couple of ways, but you can see when t goes to infinity, t squared goes to infinity, and exponential ct goes to infinity. So this is of infinity over infinity form. So which means you can use the L'Hopital's rule if you want. So let's try to use it. So this is same as limits t goes to infinity to t here over c exponential ct. So again this is of the infinity over infinity. You can apply L'Hopital's rule repeatedly. So 2 here and c squared exponential 2t here. So now in the numerator you have a constant and the denominator is going to infinity, so this limit is 0. Okay. So if you want this to be less than any number, now you can choose k to be any number, any positive number. K can be 1 or 2. Okay. So let's say this is less than So this means the function ft equals t squared is of exponential order. So as an homework exercise, check this ft equals tn, any polynomial of degree n. So this you can see, if you can keep applying L'Hopital's rule again and again, right? So this is all these polynomials are of exponential order. You can show that. So how about this part B? So take the function again, exponential t squared and divide by exponential ct. So what's this limit? CT here. So try to find these two limits. So if you want, you can have a more Okay, now let's see what's the limit here. Now this is again, you can see t squared goes to infinity, so exponential t squared goes to infinity. This is also going to infinity, so you have infinity over infinity. However, if you observe this, this is same as if I rewrite, so exponential t squared minus ct. The exponential of infinity minus infinity were kind of again undetermined form. However, if you rearrange again, this is limit t goes to infinity exponential t t minus c. Okay. Now here you should see c is a constant. So when t goes to infinity, t minus c goes to infinity, and t goes to infinity. Infinity times infinity is infinity. Exponential infinity is infinity. So this limit is infinite. Okay. Now this is an example for a function of not of exponential order. Okay. So which means exponential function, which is exponential t here, cannot beat the exponential function exponential t squared. Okay. So if t equals exponential t squared, so this is not exponential order. Then finally we have example c, exponential minus 2t. Now note that here this c doesn't matter here, right? So actually, well, you take c to be usually to be positive. So if you look at number 3, exponential minus 2t, so ft is exponential minus 2t. So let's check the ratio again. So when limit t goes to infinity, exponential minus 2t or exponential ct. So this is same as limit t goes to infinity, exponential. So if you take minus t out, you will get 2 plus c here. Okay. Now what can you say about this limit? When t goes to infinity, so exponential minus t, so this limit depends on the sign of 2 plus c. Okay. So if 2 plus c is negative, negative times negative is positive, and t goes to infinity, this goes to infinity. However, if 2 plus c is positive, positive times negative is negative, and negative t goes to infinity, that goes to 0. Okay. So this limit is this limit is 0 if this 2 plus c is strictly greater than 0. Okay. So in other words, we get a condition for c, which means if c is strictly greater than minus 2. Okay. So if c is less than minus 2, so this limit is infinity. So this function exponential minus 2t, so this is exponential order. So you need to say for this c greater than minus 2. Okay, c comes from the definition. Okay, next I just want to refresh about piecewise continuity, so let me give you a couple of questions. So each function is piecewise continuous or not. Now I think you remember what continuity means. So if you have if you are drawing this graph on a paper, if you can draw it without lifting your pencil, then it is continuous. But you have a precise mathematical definition in terms of limit, which you study in your semester 1. Here's a question. So let's say this function is f. So question is this piecewise continuous? Let's say this is 1 and part 2. We have this kind of function. So let's say this is g. So if you look at the function 1 and each p, I mean you can see both the we say this function is piecewise continuous. So this function is not piecewise continuous. Because we are here too. So here actually, I mean, I didn't put my office is at engineering now 506. Okay, and email, I think. So if you want to meet me, best thing is first email and check. Okay, next thing, there's something called causal functions. Now, what are the causal functions? So now when you do Laplace transform, you will see but some functions can be defined technically, maybe sometimes this is actually when solving some differential equations, this is actually needed. So for example, here what we mean, this kind of function. So if x is negative, we say function is 0 and non-negative values, well, you can have anything. So f is a causal function. So another name, some people say one-sided function. So if you want to draw one, quite easy. So let's say this is x, y, and this part must be 0. Okay. And after that, well, you can have anything you want. So one important causal function is what we call Heaviside function, step function, or unit step function. So this is, if you draw this, okay, now here t. Now, so values here actually at t equal 0, value, I mean, doesn't matter, but let's say this is 0 here and 1 here. So this is the Heaviside function. So this, I think in electrical setting, this is like if you have a switch and it is on, and this part is like you have a switch and it is off. Okay. So note that Heaviside function is going to be very useful. This is, you can see two properties. So one is, this is piecewise continuous, and also you can see this is causal. Okay. Okay, now here's a little exercise. Okay, can you graph these four functions now? So h is right here. So I'm asking you to graph ht minus 2 and ht sin t, ht minus pi sin t, ht minus pi sin t minus pi. So what's the graph of this one? So ht means this is 0 if t is strictly less than 0, which means this is t minus 2 less than 0, function is 0. T minus 2 less than 0 means t less than 2. Okay. So otherwise, which means t greater than 2, greater than or equal to 2, function is 1. So if you graph this one, it should look like, so let's say 2 here. So 0 until here. So then this value is 1. Or if you remember the function property, how about the next one, ht sin t? So this one, so Heaviside function is like this. So h is like this, and sine function is like this. So this is sine t, this is ht. So if you multiply, what will happen? So everything to the left side will become 0 because we are multiplying by 0, and right hand side we are multiplying by 1, so it is the same thing. So this will look like sine function here, and this part is 0. So this is ht sine t. So can you do the other two quickly? If I draw sine function first, you have something like this. So this is 2 pi here, pi here, 4 pi here. And ht minus pi. So this function shifted pi units to right, so this is 1 and this is 0. So this is ht minus pi. When you multiply, what happens? So now this function will become 0 until pi, and here this goes down, goes like that. So this is pi, 2 pi, 4 pi, this is t, so this is h t minus pi sine t. So final one. So sine functions shifted by units. So this is starting from like this. So this is sine t minus pi. And Heaviside function shifted pi units. So this is pi, this is 2 pi. So you get 1 here and 0 here. So this will look like this is pi. So this looks like this. So if you draw this straightforward, that's fine. So you should be able to work with that. So one more example, I think. So can you try this one? So we can see a function is given and it's a piecewise continuous function. So the question, what question actually asking? The function, when you can go the function, so this is different piece. So you should see I'm using the variable t here most of the time because actually when we do Laplace transform, so 0 to 3 value is 2. So value is 2, 0 to 3. So at 3 value is minus 5. 3 to 4 value is minus 5. And value is 3. So after 4 value is 3. So this is well clearly defined this by this piecewise. Okay, so let me show you. So GT, so if you start with the Heaviside function, so left hand side now, actually here it is not given, but if you want, you can assume say value may be 0. So if t less than or equal to 0, okay. So gt, let's say 2 times Heaviside function. Okay, but now this is 2 for all positive values, right? But we need the value until 3 only. So we want to do something at 3. Okay, so take again the Heaviside function h and shift this 3 units to right, so t minus 3. Okay, so then what you can do, we want to, the function after that must go down, value actually minus 5. So we want to add something which will put this down, so, and value must be minus 5. Right now value is 2, so add minus 7. So note that before 3, now this does not affect anything. Before 3, the second part, value is 0, after 3 value is minus 7, minus 7 on the value is 2 on the value is 5 after 3, but we need value this to be minus 5 only until 4, so we again need to adjust at 4. So we want to add this another something Heaviside function after 4. So take the Heaviside function now being shifted by 4 units, add this. Now right now value is minus 5 at 4, it should go up to 3. So how much you need to add? From minus 5 to go to 3 you need to add 8. Okay. So this is 2 times Heaviside function minus 7 times Heaviside function ht minus 3 plus 8 ht minus 4. Okay. So this is what I asked. Now you can see gt is now being defined without graph this one. Well, I mean, answer is right here. You should get this one, but in your brain you should see how to get that one from this way. So if you don't have a calculator, so I am asking you to do this using logarithms, so maybe you don't have logarithms. So if you try to do this, say if you take logarithm of these two numbers, so this will become logarithm this number, so this may be difficult, but addition here is easy. Okay, so that's basically the idea. Once you use a transform, the thing is to make things easier. So that's exactly what's happening with the Laplace transform. When you do differential equations, you remember so that's why the basic idea behind transformations, you move from one setting to another, now things are easy. Okay. So in general, integral transform, so this means say you are given some function, let's say this is given to you, little f, so f is given, and well this is called the kernel. So by the way, this is not the kernel in the army. Okay, in mathematics integral transforms, you take this function k. Note that k is a function of two variables. Okay, so the f is a function of t, kernel is function of s and t. So s is now a new variable. Multiply these two, integrate from a to b, and note that your result does not now depend on t. There is no t, however there is s, right? So left hand side you will see you have s here, not t. Okay, so f is given, so this given f as, let's say, domain t, it's in t domain, so basically you can think as time domain, t as time. Okay, and your result capital F, so note that it has domain S. So often this is in electrical, this is frequency domain. Now for our purposes t is real, I mean usually t is greater than or equal to 0 because it is time, and in general this s can be complex actually. Okay, so which means s can be written as like sigma plus I omega. So I think omega here, omega becomes frequency and sigma is amplitude, I think. But in mathematically we don't want to go into that much detail. So when you study these things in your electrical classes, you will study the interpretations. So for us in this class, t is one variable, all you need to know, s is another variable. Okay, so the f is one function, capital F is another function with a different domain. So some transformation is happening. Now for this class, so we keep s real, so which means this s we treat as a real number. Okay, but the rest of the things will be very similar. So once you understand this, you can, when your practical application things, you can do other things. And here this is defined from a to b. However, it is possible b can be infinity, this is possible, and sometimes a can be minus infinity, also possible. Okay, so important thing is the difference in the domain. We are shifting from actually time domain to frequency domain with this transform. Okay. So, well, in general, this is what is happening. Now, when it comes to Laplace transform, exactly it is this. Now, some notation is going on here. Now, again, note that given function is ft here, and note that you are multiplying by exponential minus st. Now, for us here, I have put here s as a real number. Okay. So S is real. So given function is f, that's the function of t, and you multiply by the number which is exponential minus t, and integrate of t over t. Now as I mentioned, that time. So in this third example, when c less than or equal to minus 2, so which means here this s is becoming the value here you can think as x is having value 2, right, some particular value for s. So it may converge or diverge because it's an improper integral. Now this theorem tells when this will converge. Now this is a theorem. So usually in a mathematics class, what comes next? You should know the theorem here so that you get some idea. See, we want to calculate this, right, 0 to infinity. So ft exponential minus st dt. So what we do, say, let's say we integrate 0 to t ft minus st dt and t to infinity. So I'm separating the integral, okay, into two parts. So this is just the idea. Now if you look at the left hand side, the first part here, so note that this exists. So what's the reason? Because this is a finite interval 0 to t, exponential function is continuous function, and you can integrate well from a to whatever the discontinuity from that point to the next point and that point. So since f is piecewise continuous, and the second part, so this part exists because actually f is of exponential order. So if you take the absolute value here, now I'm not going to all the rigorous details, but just to give you the idea. So you can check, because f is of exponential order. Now here this is exponential, st is positive. So if you multiply by exponential minus st, both sides positive number, you get this inequality. Okay. So this is same as, this is k exponential. If you have minus s minus ct, this is what you have. Now if you integrate this right hand side, this integral converges whenever this value is strictly greater than 0. Okay. So which means this. So if you integrate 0 to infinity exponential, so this one you can check, I mean you did a similar calculation earlier. So this will converge if, converge means this becomes actually upper limit will become 0. So this converges this x minus c is strictly greater than 0. So in other words, s should be greater than c. So that's where this condition comes here. So this is the reason I want to give this detail, because otherwise you don't know. Okay, now is the time for you to enjoy yourself. So you can solve some fine Laplace transforms. So you are going to do something very we will start with the very basic. So let me go down. So we want to find Laplace transform of 1. Okay, now note that this 1 means the function 1, okay, not the number 1. So this is the function f of t equals 1. Okay. So now this constant function is defined for all real values. So some people, because of that, they may say find Laplace transform of well, basically the Heaviside function here. So these things are the same, right? So anyway, how do you find this? Let's say L1. So our definition, 0 to infinity we integrate, function is 1, multiply by the kernel, exponential minus st integrate. So quite easy thing to do. So can you find this? So in this integration, note that we are integrating with respect to t and s to t plus 4. here what you have is exponential minus st minus s, limits are 0 to infinity. So upper limit when t is infinity, note that s is, well, what that limit? So t goes to infinity, that's minus I and s is also diverging integral. So we put the condition s to be greater than 0. Okay. So if s is positive, so upper limit here is going to be 0 and lower limit, so this is exponential 0 is 1, so 1 over this is minus s. Okay. So answer is 1 over s. So note that Laplace transform of 1, which means the constant function, so is 1 over s and s is strictly greater than 0. So this may be something you should remember, especially if you are electrical student. So is that clear how we do it? If you are not sure, you may want to write a couple of steps here. So if you are not sure, see note how we do here. A goes to infinity, exponential minus so s a over minus s, right? And you get 1 over minus s. Okay. So now that when s is positive, this goes to 0. So here s you can take out, say minus 1 over s. Exponential minus s, say this is what you have. This is plus 1 over s. What you are saying is this limit is 0. So if we have this condition, s is positive. So that's what we are using. So if you have done this, you should try the other one, ht exponential at. So please try to do that by yourself. So in this next one, see, we want to find Laplace transform of ht exponential at. So note that this is same even if it is given, or find Laplace transform of exponential at. Right, so some people may say with this Heaviside function notation, so this equals so integrate 0 to infinity exponential at multiplied by exponential minus st dt. This is 0 to infinity exponential, let's put this as s minus a. So if you integrate, you get exponential minus s minus a t over minus s minus a, and limits are 0 and infinity. Now again, see what's happening. If you understood what you did in earlier question, note that when t goes to infinity, so minus sign here, we need s minus a to be positive, so that that limit goes to 0. Okay, so we take the condition s minus a to be strictly greater than 0. So with this condition, so if you assume this is strictly greater than 0, then your upper limit is going to be 0. So this limit is 0 minus, when this is t is 0, this is 1, so 1 over minus s minus a. So answer is 1 over s minus a. Okay. So this means Laplace transform of exponential a t, so is 1 over s minus a with s strictly greater than a. Okay. function is psi a. So note that all these Laplace transforms are available in this table. Okay. So later you will, most of you will remember. We are here. So for to find fs, when fs will be, so integrate 0 to infinity, given function is sin at, so multiply this exponential minus st dt. Can you do this integration and find what is How you do this? Let's say we do integration by parts. So anti-derivative, let's say you do exponential minus st, integrate this and sin at, so limit 0 to infinity, minus you have 0 to infinity, so differentiate this, get a cosine at dt. Now look at this. So upper limit here, so sine function is oscillating function between 0 and 1. Okay, so everything depends on this exponential function. So it is very quite easily, once you put this limit, exponential minus st, upper limit, right? If SC is positive, this will go to 0 very quickly. Okay, so now if you are not sure what I am saying, let's say you have sine function for the positive part may be like this, it goes like that, and this exponential function, so minus exponential minus st, if s is positive, like this, so something like this, right? It goes to 0 very fast. So this is sine, let's say sine 80, this is exponential minus st when s is positive. So when you multiply, what will happen? So let's not worry about what's happening when this is the negative time. So here this is 0, so anything can happen here, but after that this is going to be, so it goes like this, okay, goes to 0 very fast. So when you put the upper limit here, if s is positive, you get this limit to be 0. Okay, so which means if I write down again in detail, so which means you have exponential minus sa, this is sin aa here, minus s, then lower limit, sin 0 is 0, exponential 0 is 1, so that is 0, so this limit is 0. So what we are saying is this limit is 0 if you take this s to be greater than 0. Okay, so now this is the condition we are going to impose here. Now this part we have, so minus here it become plus a over s, 0 to infinity exponential minus st cosine at dt. So you have a over s. So again do the integration by parts. So you have exponential minus st or minus s cosine at, now limits are 0 to infinity. So this is minus 0 to infinity exponential minus st over minus s. So derivative here minus a sin at dt. So now we'll see what you have here. So look at this limit again, just following the same argument. Upper limit will be 0. Okay, same way. So upper limit is 0 here, and lower limit cosine 0 is not that 1, and exponential 0 is 1. So you get 1 over L minus S. Okay, so that is this part. Then here 3 negative signs, you have A over S, 0 to infinity, exponential minus st sin at dt. So if you remember what we started with, this is our f of s. Okay, so let me use the space below here. So what we have here now, f of s equals a over, so this is positive s squared, so this is minus a squared over s squared f of s. So now you can solve for f of s. Okay. So I think you can do the algebra part here. So f of s, and this is s squared plus a squared equals a. So you find f of s to be a over a squared plus s squared. Okay. Now note that here if you look at this expression, so this is true for less, right? A over a squared plus s squared, that doesn't matter, this is defined for all values of s. However, we impose this condition to get the limit, right? So something happened in between on our way. So which means our Laplace transform of sin at, so this is a over a squared plus s squared. However, remember this condition s must be greater than 0. Okay. So in your practical applications, of course, it may be automatically greater than 0. But in mathematical, so next example here, what we are asking is to find the ramp function, which is a Laplace transform of ramp function. Well, this is basically asking to find the Laplace transform of t, but if you draw this, this looks like a ramp, right? This one. So RT equals T HT. So positive part H is 1, so it is just T, so goes like this. And for the negative part, this becomes 0. Instead of T, it is 0, so it looks like a ramp, so that's why I say ramp function. So I leave that part as an homework question, I think. So please complete this. Now I have written things here. So but this exercise 10 is, let's say, homework. Find Laplace transform of THT. Okay. So you can check the answer in the Laplace transform table. I think maybe I didn't put in concept, but I can put it in the concept. Okay. Okay, now next thing is here, the main topic is main subtopic is finding the inverse Laplace transform. But for some final fun, maybe you can try what is the Laplace transform of this guy. So note that you want to integrate 0 to infinity. So this is 1 over root t. So exponential minus st dt. So how are you going to do this integration? try a substitution. Let's say st equals something, tau or something. So try this substitution as a homework question and see what you can do. I'll explain a little bit maybe next lecture if you want. We want to start with the inverse Laplace transform. So basically it's kind of easy business because we are going to depend on a table. Okay, so we will stop here. If anybody has any questions, you can talk to me right now. So thank you, and I'll see you next week.